This sound file contains the spoken version of a Wikipedia article on Babinet's principle, recorded by user Abacate Abacaxi. The material recorded is current as on the 21st of March 2011. In physics, Babinet's principle is a theorem concerning diffraction that states that diffraction pattern of an opaque body is identical to that from a hole of the same size and shape, except from the overall forward band intensity. Contents: 1. Explanation. 2. Demonstration experiment. 3. Radio engineer useful formula. 4. See also. Section 1. Explanation. Let B be the original diffracting body, and B plus its complement, the body that is transparent where B is opaque, and opaque where B is transparent. The sum of the radiation patterns caused by B and B plus must be the same as the radiation pattern of the undisturbed beam. In places where the undisturbed beam would not have reached, this means that the amplitudes of the radiation patterns caused by B and B plus must be opposite in phase but equal in amplitude. Diffraction patterns from apertures of bodies of known size and shape are compared with the pattern from the object to be measured. For instance, the size of red blood cells can be found by comparing their diffraction pattern with an array of small holes. One consequence of Babinet's principle is a paradox that in the diffraction limit, the radiation removed from the beam due to a particle is equal to twice the particle's cross-section times the flux. This is because the amount of radiation absorbed or reflected is the same as the amount diffracted. The principle is most often used in optics, but it's also true for other forms of electromagnetic radiation, and is in fact a general theorem of diffraction and holds true for all waves. Babinet's principle finds most use in its ability to detect equivalence in size and shape. Section 2. Demonstration experiments. The effect can be simply observed by using a laser. First, place a thin, approximately 0.1 mm, wire into the laser beam and observe the diffraction pattern. Then observe the diffraction pattern when the laser is shone through a narrow slit. The slit can be made either by using a laser printer or a photocopier to print onto clear plastic film, or by using a pen to draw a line on a piece of glass that has been smoked over a candle flame. Section 3. Radio engineer useful formula. Babinet's principle can be used to find complementary impedances. Babinet's principle states in optics that when a field behind a screen with an opening is added to the field of a complementary structure, that is, a shape covering the screen hole, then the sum is equal to the field where there is no screen. Demonstration can be found in any good optic or antenna book, such as Balanès, Cross, Stutzman. The end result, corollary as a matter of fact, of practical interest for antenna engineers is the following formula: Z metal times Z spot equals eta square divided by 4, where Z metal and Z slot are input impedances of the metal and slot radiation pieces, and eta is the intrinsic impedance of the media in which the structure is immersed. In addition, Z slot is not only the impedance of the slot, but can be viewed as the complementary structure impedance, a dipole or loop in many cases. In addition, Z-metal is often referred to as Z-screen, where the screen comes from the optical definition. It is noteworthy that the thin sheet or screen does not have to be metal, but rather any material that supports a J vector, current density vector, loading to a magnetic potential A vector. One issue with this equation is that the screen must be relatively thin to the given wavelength or range thereof. If it is not, in case modes can begin to form or fringing fields may no longer be negligible. For a more general definition of eta, or intrinsic impedance, eta equals square root of mi divided by epsilon, where mi is the magnetic permeability and epsilon is the electric permissivity. Please note that Babinet's principle does not account for polarization. In 1946, H. G. Booker published slot areals and their relation to complementary wear areals to extend Babinet's principle to account for polarization, otherwise known as Booker's extension. This information is drawn from, as stated above, Balin's 3rd edition antenna theory textbook. Section 4. See also bistatic radar. We now come to the end of the spoken article Babinet's Principle. The sound file and all text in this article are licensed under the Creative Commons Attribution Share Alike 3.0 Unported License, available at http://creativecommons.org/license/by-sa/3.0.